Hi, my name's Nick Suzo. I'm going to take you through an introduction to machine learning over the next few weeks. So you've learned a lot already about regressions and other statistical analyses, and we're going to just take that a little step further, where instead of doing simple regressions that we've been doing so far, we're going to look at how machines use regressions at a huge scale. Basically, all machine learning is, to demystify it, is a whole bunch of regressions. We have the computational power to just instruct the machines to keep running regressions until they find their most accurate patterns from the data. Essentially, demystified, that's all machine learning really is. Before we get there, so my name's Nick. I'm a professor in the law school. I study the regulation of digital technologies. We've got a center of excellence in automated decision-making that just launched. And so one of the big priorities for me over the next 7 years and the life of that center is to try to understand not just the ethics of AI, but how we might start to create the institutional, by which I mean legal and cultural protections for basic fundamental rights and ethical standards for intelligent machines. This is going to be this is obviously a global challenge. Lots of people are really concerned about how exactly decisions are made and how where they might not be accountable, or where they might not be accurate, or where they might be biased, and particularly where they might reinforce existing social inequity. So, but still at this stage, we don't really know what to do about it. We find it hard still to even talk about in simple terms what it is that machine learning algorithms are doing and what impact they might have, let alone starting to understand how we might measure that disparate impact, how we might evaluate the risk that's latent behind what are typically black box models, how we and what sort of procedures we might put in place to mitigate those risks. So in this week, I want to focus on the basic vocabulary of machine learning. I want to talk about how we understand what a model is and what it does. You've already, I presume, done the readings for this week. If you haven't, go do them. Go watch the introductory videos where you'll get an idea for the basic terms that we're going to talk about now. I'm just going to run you through a quick application of those terms in the context of a particular model. I just want to get in the habit of using the vocabulary of machine learning to demystify it and to ensure that we can have productive conversations with data scientists and with regulators who are going to be interested in deploying or monitoring these sorts of models. I'm not asking you in this unit to become full-fledged data scientists or mathematicians capable of designing or even understanding the complex maths that goes on in a machine learning algorithm. But what I do want, by the time you finish this unit, is to give you the vocabulary you needed, the basic understanding to be able to have a conversation about how a machine is trained, how a particular algorithm is trained, what sort of decisions or what sort of predictions it produces, where the risk might be that is hidden in either the data collection or the design of the algorithm, and how we might evaluate those risks for accuracy, but also for bias and fairness and so on. So the first exercise that I've set this week is I'd like you, over the next few days, in advance of our stats lab, to come up with an example. It's hard to not see examples of machine learning. They're in the news all the time. Come up with one and think and answer these questions just to get in the habit of explaining how a machine learning system works. I want to get out of the habit of thinking about machine learning algorithms as black boxes that we can't possibly know, that eat up some data and do some magic and spit out some sort of response. And I want to really pay attention to the quality of that data, the type of prediction that's being made, how that's being evaluated, and how it relates to the question that we're asking of the model. So my example is the COVID-19 predictions produced by Google. Google creates a 14-day forecast by state in the US of the number of deaths expected due to COVID-19 over the next 2 weeks. Clearly, this is narrow AI, of course. It's not super intelligent general AI. It is a machine learning system that learns from supervised data because it's got historical data about, if you look here, clearly the machine is fed historical data about the number of deaths and the number of confirmed cases, and it's asked to predict future confirmed cases or future cases and future predicted deaths. Sorry for the grim subject matter, but this is a really important application of AI that has a lot of relevance for people working in governments and in health organizations and institutions right now. Importantly, you see that, let me just get out of this breakdown. Can I get out of this breakdown? And sorry, I've managed to break my visualization. Here we go. So you see here that in addition to number of deaths, the algorithm here is forecasting confirmed cases, hospitalizations, the number of people who will need an ICU bed, and the number of people who will need a ventilator. So you can immediately see that this is going to be of huge interest to hospitals and governments who need to understand what's going on in order to plan for the immediate future. So the predictions here, we can immediately see what they might be used for. So what type of a machine learning system is this? It's a supervised algorithm, as we said, because it's learning from historical data that is labeled. We already know if we feed it the data over the last 6 months, we know how many people were hospitalized, how many people needed a ventilator, and so on. And it's a regression algorithm because it's trying to extrapolate from those continuous numbers a prediction. And here we've got a prediction line over the next 2 weeks of the number of deaths that we expect given the historical data that we have, that Google has fed into the machine. So essentially, this is just a whole bunch of regressions that the machine is trying to learn the patterns from the historical data sets, just like we did over the last few weeks, but it's just running a great many of regressions over and over again, trying to get its predictions as accurate as possible, measuring it against the information that we already have available. So typically that'll be split into a training set and a test set, a few others as well, but you don't need to go into too much of the technical details. And the machine tries to learn from the training sets, and then it evaluates its own performance against the test set. And so Google would have set a way to measure the performance of the model, so to give that feedback to the model as it goes through, and it will optimize usually to minimize the error between its predictions and the accurate predictions that we know from the past. Okay, so it is a supervised regression machine learning algorithm. It is aiming to predict outcomes. It tells us nothing about causality. It's just giving us a number based on patterns that it's discovered. How is it doing it? That's the next question. There's not much information here. You need to go into the user guide to get information about the data. And from the user guide, you end up finding, I think, if you look closely enough, a white paper. Where have they hidden it? They don't make it particularly easy to find, unfortunately. There it is, white paper, which gives you some of the technical details of the model. All right, so here we go. We can start to understand how exactly this machine learning model works. So maybe the first question that I asked is it a deep learning model? We use the term deep learning to talk about things like neural networks, essentially. You can think of a normal regression is a fairly simple way to learn patterns from the data. If you create stacks of regressions and you put them all together and you teach the machine how to learn from the regressions that have been done in previous layers, you can stack all of them together and come up with a more sophisticated way to learn patterns from the data in the output. This is obviously a lot more computationally intensive, but deep learning has given us a lot of breakthroughs in terms of the sorts of patterns that we can identify from existing data. So here we are dealing with a deep learning model. I'm not going to go into too much information, too much depth here, but it's clearly a deep learning model that learns from documented cases, documented information about recovered people who have been infected, and people, unfortunately, who have died, or people who have been hospitalized. Subset of those have required an ICU, subset of those have required a ventilator. You get here a compartmental model. I think that means that Google is categorizing people into different compartments here. The class of people who have recovered, the class of people who are infected, and so on, and using that to train the model in some way. I don't know beyond that how these compartmental models work, and you don't need to either at this stage, except to understand where is the data coming from and how is it running. So you see, as we keep going down, there's a lot of information here that I'm certainly not going through the maths because I don't understand these maths. As I said earlier, I want us to be able to learn, to understand the vocabulary in English. I don't want us to be able to actually design or critique and prove the accuracy of models at the mathematical level. What we need to know is where is it getting its data from and how accurate are its predictions. So the data, it turns out, in this case, is aggregated from a whole bunch of different sources. Here is Google's COVID-19 open data system. And we have here an explanation of where the information comes from. It turns out that some of it comes from the New York Times, that they've got reporters on the ground throughout the US who are collating all of the official statements and asking follow-up questions, and doing that on a daily level that contributes to a large COVID-19 dataset. And then you've also got direct reporting from hospitals about cases and states about aggregated cases and outcomes from cases. So the first question here then, if that's where the data comes from, what are the potential limitations? And we can even download some of the data here and look at it in detail if you want, but let's not worry about that right now. Let's just think about what the limitations of this model might be. So your first limitation that you always think about is where the missing data is, where the data that you do have comes from, and what its limitations might be. One of the challenges in this area is that we might have decent information, reliable information from states, from regions, from hospitals, but we can't accurately count cases, right? There are a lot of unconfirmed, maybe cases that that are asymptomatic or that people are not going to get tests for, and it's hard to know the true rate of COVID-19 infection in the population. What we do have is confirmed cases. We have then some extra information that Google feeds into this model. It has some sort of mobility data set that it tries to understand how people move around. It has a data set that deals with public policy decisions. If you're dealing with the US, you have 50 different states and other localities that are all implementing different policies. And so those are important to take into account in this model to try to come up with an accurate prediction for the future. Then you've got demographic information, because we know that the virus affects people, different people differently. And you've got other information here, historical air quality, some economic information, the capacity of hospitals, and then finally the confirmed case counts and death counts for each of the states that they are looking for. So with all of this, they are trying to come up with a number that represents the number of cases that they predict over the next 14 days and the predicted utilization of hospital beds and ICUs and ventilators over the next 14 days. Cool. So that's a pretty cool model. It's interesting. The last question I asked you to describe about a model is what is it optimizing? Here it's trying to predict, as I said, these 5 things. This is again a regression that tries to accurately predict. And the way that it does that, by the looks of it, is that it is optimizing for error on past predictions. So what happens here is that we have you run the system, you've got the past predictions, and you probably run it maybe every day and or even multiple times a day. And you hold out some of the data. So you might run it this week, and you're only generating predictions, or you only feed it data up until this time last month. And then you ask the machine to predict, based on what it's learned, what it would predict in terms of number of cases and number of deaths over the last month. And that's important because we have actual labeled data for the last month. We don't have any for the future. So the way that these systems work is you split the data set into training data, internal validation data, and external test data. The machine never sees the test or shouldn't ever see the results, the answers to the test data. So you train it, say to the end of August, and then you say, give me your predictions for September, and you measure the accuracy of those predictions against the actual figures for September. What we would do with a large model like this is make it automatically optimize to improve that error rate. So this is where what we call validation data comes from. The machine is allowed to look at the answers for the validation set. And as part of its training loop, because essentially it's just going over and over and over, trying to learn patterns from the same set of data and trying to refine how well it understands those patterns. So the validation set gives it the answer to the things that it's trying to predict. So in this case, it would be trying to predict September data, and it would then look at its performance over the actual labels, the true labels for September, and take a slightly different approach each time. And eventually, it keeps on selecting the patterns that lead it to the most accurate predictions. And it might do this thousands, hundreds of thousands of times to narrow in on the most accurate measures it can develop for predictions over the last, say, month. Then, once the machine's learnt all that it can, we can then evaluate it manually based on the test data that it shouldn't have seen and come up with an accuracy rate. And if we're happy with the performance, you would look at then generating a prospective prediction for, in this case, hospitalizations over October that we don't have a clear answer for. So that's when we talk about objective functions, the purpose of the model, what it's trying to do is predict hospitalization and utilization and confirmed cases and deaths over the next 14 days. And the way that it's doing that is that it's optimizing probably for error rates, average error rates over the previous predictions. So it looks at what it would have predicted over the last few weeks and tests that and keeps working until it is able to minimize the errors that it makes. All right. So that's what I'd like you to do. That's pretty simple, really. I just want to, again, get in the habit of talking about models. So I want you to bring your own model, bring your example, post it in Slack, and tell me, is it supervised or is it unsupervised? Is it a deep neural network-based model or is it a shallow regression? What sort of model is it? Does it do classification? Does it do regression? Does it do clustering or feature extraction? You've got the definitions of all of that in your reading, so you should be able to work out from the model that you picked what type of predictions or outputs it is providing. Here again, we've got a regression model because it's trying to predict a continuous variable. Where does the training data come from, and what might the limitations be, and what is the model optimizing? How does it know when it's got the right results, and what do its designers think that it is actually predicting? All right, so have a go at that. Upload it, send it to us on Slack. We'll talk a little bit about some of the examples when we get to the Stats Lab in person. But in the meantime, let's have a conversation about some examples over on Slack. It'll be fun. These are obviously areas where there's a lot of interest in the news. So I look forward to seeing what you come up with.